Hello, Tom. Tom is an engineer on the Planetary Computer team at Microsoft. He helps maintain several libraries, including Dask and pandas. And today, Tom will talk about scalable sustainability with the Planetary Computer.
All right, thank you. So let's get started. First of all, I want to kind of set some context, where I'm coming from, like why is someone from Microsoft at a PyData talking about sustainability? And so last year and a half ago or 2 years ago, Microsoft made a few sustainability commitments. These are things for like their own business that they're concerned about, things like being carbon negative, water positive, zero waste by 2030. I'll put links up at the end, but these are all links to the announcements for these, all these commitments. And then the last commitment here is around protecting our ecosystems. So that's some concrete things like setting aside more land than we use by 2025. And then this last thing here is build a planetary computer. And as you're going through this list, one of these is definitely very different from the others. So things like being carbon negative, water positive, zero waste, like that's, very concretely like acknowledging Microsoft's impact on the climate. And then really interested in like what the changing climate, the kind of risks that poses to our business and to the businesses of our customers. So you kind of see why we're interested in things like this. But this last one around like building a planetary computer, what is that? Planetary computer for a sustainable future, pretty picture. End of the day, planetary computer, it's this nice term that we're using for this thing that's like, it's worth recognizing that a whole lot of sustainability problems, they look a lot like geospatial data analysis problems, where you have lots and lots of geospatial data coming in that people want to use to make informed sustainability decisions. So that's essentially what the planetary computer is. It's like this geospatial analysis thing to help people analyze all this data for sustainability. If you break it into its components, the main thing that makes up the planetary computer is the data catalog. So this is a whole bunch of data in Azure Blob Storage in nice analysis-ready, cloud-optimized formats that people can just go and use. And it's like, that's great, that's a lot of work. We also have APIs that we build on top of that data to make it easier to use. And we'll see examples of that in a minute. And then finally is the Planetary Computer Hub. So this is like a convenient environment where people can go and do their analysis. So this is taking a lot of the lessons learned by the Pangeo community, if you're familiar with that group. They've basically been trying to do scalable geoscience, mostly on the cloud, not exclusively, and have been just like smoothing over a lot of the rough edges, figuring out what works, what doesn't, when trying to do geoscience at scale. Finally, kind of recognizing that it's not just doing data analysis for its own sake. All of these, all the data that we're putting together, the APIs and the hub, they're all kind of in service of sustainability decision-making. So to that end, we're partnering with other groups and individuals to make applications that use our data, our APIs, insights from the hub to put together higher level applications that can then be put in front of environmental sustainability decision makers to help them make informed decisions. Okay, so diving into each of these, starting off with the data catalog. I'll just pause on this slide for a bit because it's so nice to look at. Every time we bring on a new data set, we get to make like a thumbnail for that. So it's really the best part of adding a new data set. So we have lots and lots of data, like I said, in Azure Blob Storage. So this is nice, kind of jumping ahead, but Blob Storage is like very scalable. So it's you can access it in parallel from many machines if you have really large problems. So it's really nice to be able to rely on that scalability and that parallelism. And we don't want anything in between your analysis and Blob Storage. And then we have it in cloud optimized format. So depending on the type of data, that's going to look a bit different. In the case of raster data, it's like imagery, remote sensing data coming from satellites or aerial photography, or like elevation data sets derived from that imagery, those are going to be stored in as COGs, so cloud optimized GeoTIFFs. If you're not familiar with geospatial data formats, a COG, a cloud optimized GeoTIFF, is just a TIFF with some geospatial metadata in the header that's been kind of internally chunked in certain ways to make it friendly for streaming over the web. Okay, but end of the day, it's just like a TIFF file, so an actual image file in a special format. For Earth system science data, so it's like climate and weather models, we're using a lot of Zarr. So climate and weather models, they tend to be higher dimensional than imagery. And so they're best represented as chunked in-dimensional arrays. And Zarr is a great format for that. And then finally, for tabular data, we're mostly storing that in Apache Parquet format. And we have nice readers like Fast Parquet and PyArrow for being able to read that in Python. But all of these all these storage formats are language agnostic. And like I mentioned earlier, we're really focused on these cloud native style workflows. So part of that is just putting the compute and the data in the same region. So this is something that Pangeo group has been working on for a while now, but enabling these kinds of workflows make it easy to set up compute in the same region as the storage and then access it in parallel. Stream data directly from blob storage straight into memory, either on a single machine or possibly on many machines, as we'll see. Okay, so the next little section, we saw the data catalog, then we have the APIs. So in particular, we're going to be talking about STAC, the Spatial Temporal Asset Catalog, and what it enables. Before I get into what STAC is, it's worth kind of talking through like, why is it helpful? So let's say, we've gone through all this work, we've gotten this data, they're beautiful cloud optimized GeoTIFFs, perfectly optimized, and they're in blob storage for you. And then I ask you to say, okay, give me all the COGs that cover Wyoming in 2016. And you're looking through the list of COGs in blob storage, and you're like maybe opening up the Python regex documentation to see, there's dates in here somewhere. It's like a lot of dates. I'm not quite sure. There's probably some geospatial, like where on Earth this is, but it's kind of not exactly obvious just by looking at the file path. So you're probably going to have to like open up these files with rasterio and like figure out what's its like coordinate reference system, what area it's covering, things like that. So that's slow, that's error prone. If you want to, this is for Landsat 8. If you want to do the same thing for a different mission like Sentinel-2, that's going to have a different naming scheme. And so you have to like reinvent all those heuristics to find like, how do I get just the ones that I care about? So that's where STAC is helpful. If you're with a STAC API, like we are running here at planetarycomputer.microsoft.com, you're able to use these client libraries like PyStack client. And then that task of give me all the images for Wyoming in 2016 becomes very easy. Just ask for this Landsat 8 collection 2, level 2, that intersects with this Wyoming geometry, GeoJSON object, and then covering this date time here, this date range. Okay, so that's really what STAC is enabling. In terms of what it actually is, it's this specification for how to catalog the metadata associated with geospatial scenes, spatial temporal data. Okay, so the core STAC spec says basic things about like this scene, this image was captured at this date time, and it covers this area, things like that. And then there's a whole list of extensions, like what's the projection information, what area on Earth does it cover in that projection, things like that, that's built on top of STAC and we're using for these workloads I'll show you later on. In terms of, this is way too small to see, but just kind of emphasizing that STAC is a metadata standard. So it's taking all of that metadata that's associated with like a satellite image of the Earth and putting it into a structured form. So it's all about the metadata. And then that is linking to the actual assets themselves, which might be COG files, they might be Parquet data sets, it can be whatever. But the actual STAC is just concerned with metadata, and then it has links out to the data files themselves. So with all that structure, we're able to do some interesting things on top of it. So like one interesting thing is building that search endpoint. And so that's what's powering the search endpoint. We're also able to do things like build a nice HTML catalog at planetarycomputer.microsoft.com, and the Explorer, which I'll show if I have time at the end. Okay, so that's the data, that's the APIs, and then the last thing here is the Planetary Computer Hub. This really is building off those lessons learned by Pangeo. So I'll jump over to it now. And hopefully, yeah, so I'm logged in here to this Planetary Computer Hub. And this is just a JupyterHub deployment in Azure in the same region as the data. And it's enabled with Dask Gateway. So if you haven't used Dask Gateway before, it's a way to have like the centrally managed Dask clusters for users. So I asked for a gateway cluster here. I scale it up to 64 workers, and then I'm ready to go. So this first example we're going to go through is computing a cloud-free composite. So when you're working with satellite data, the first thing you always run into is, at least for electro-optical data, is it's cloudy a lot of the time on Earth, and that just kind of ruins anything you're trying to look at. So one common operation is to kind of stack up these images in time and do like some kind of median to remove the cloudy pixels. Okay, so using what we saw before, we're going to go to use our STAC API here, and we're going to, in this case, use Sentinel-2 scenes to find all of the Sentinel-2 scenes that intersect with our bounding box here. So this covers Redmond, Washington. For this date time, so 2016 to the end of 2020, and where the STAC enables you to catalog a whole bunch of information, and then the STAC API lets you filter on that. So in this case, we're going to filter where the cloud cover, as determined by ESA, the European Space Agency that's running this mission, where the cloud cover is less than 25. Okay, so we can run that, and we quickly, like in less than a second or so, we get back the 138 items that match our conditions. So the API here, this is, anybody can use this. It's completely public. Anybody can make requests to that. The data files themselves, so the COG files, those are in a private blob storage account. So if I just tried to open up one of those URLs, I'd get like a 404 error. So you do need to sign the URLs before you can access the data. And you can sign the URLs anonymously. It just depends this read-only shared access signature to the URLs. And at that point, it's a regular URL that you can open up in any common tool, QGIS, GDAL, Rasterio, whatever. And yeah, at that point, it's just a regular URL. We're going to use a tool called STAC, which makes it easy to stack together a stack of stack items. If you notice, I ran that and it was like very quickly returned the outcome of this cell. So what STAC was able to do is quickly build up this X-ray data array. So we have our 138 time steps here, our 3 bands. So we're grabbing red, green, and blue band. And then our X and our Y coordinates. So STAC is building off of all of that stack metadata. So it has things like the projection information and the shape and the size and all of that. It's able to use all that metadata to construct this data array without opening a single file, a single COG file, which takes like a handful of a few hundred milliseconds maybe. And when you have 138 times 3, that few hundred milliseconds adds up. And then so it's able to do that real quickly, and then we're actually persisting the data. So if you haven't seen Dask before, this is the task stream. So vertically, these are all of our workers here, and going to the right, this is the activity of a core on our cluster over time. So right now, we're just reading data, essentially. It takes like 6 to 9 seconds maybe to read in a single COG file. Okay. And now we want to do our cloud-free mosaic by taking a median. And so this will kind of collapse over the time dimension. Before we had those 138 time periods. We're going to take the median at each pixel and then convert that to a true color image, with the idea being, so the idea behind the median is like things like buildings and like hills, mountains, roads, they tend to not change much snapshot to snapshot over time. But things like clouds will come and go. So this is a pretty common way to remove clouds from a stack of images. Okay, so that's gonna carry on there. We're doing, so for Dask, when it does this median, there's a bunch of rechunking to get the time coordinate in one chunk and rechunking along the other dimensions, but it finishes up the median pretty quickly. And then now I think we've moved on to converting that 3D array of red, green, blue in, I think it's like floating point from 0 to a few thousand or something. I don't know exactly what the meaning of those pixels are, but this X-ray spatial true color will convert it to a RGBA representation. At that point, you can plot on a map using things like matplotlib and any of those tools. In this case, we're going to try STAC has a handy little helper function called stack.show, which lets you put it onto a leaflet map. So I'll go full screen here in a sec, but as I pan and zoom around, we have all this data out on a cluster as like this RGB image that's in a bunch of chunks on the cluster. And stack is able to say, look at it, what area are you looking at? And then find that window, where are those images on the cluster, and then bring back just that. So, and the other thing it's able to do is as I zoom out, it's able to go to like lower resolution, upsample. So that's nice and quick. But when I zoom in, it'll snap to with the higher resolution imagery. Hopefully in just a second. I'll wait for a minute or so, but there's a bunch of computation happening on the cluster right now. There it goes. Okay. All righty. So that is an example of remote sensing, or a quick little median on some imagery. The nice thing about X-ray is like it's this general purpose domain agnostic library. So maybe you don't want to combine images from January with images from July. They're different seasons. So you can do things like group by time.month. So X-ray has this nice high level API for grouping and then doing operations to each group. And we're able to build on that for our domain specific application of making this cloud-free composite. Okay, so that median computation, that per month median computation finished pretty quick, and now we're pulling it back locally to this notebook, the client. And then we'll again do the true color transformation from whatever units it's in originally to RGBA. I'm gonna skip over this section just for now. It's gonna take like 30 seconds or so, but end of the day, we'll get a series of images using X-ray, and yeah, for one per month. As I wait for that to actually render, I'll start to introduce the next section just for time. Oh, I have a typo here, animating Hurricane Florence. So animating, yeah. So this example is building off this example from PyTroll, which is this library for working with satellite imagery. Yeah, various satellite imagery. Here's our picture. So you can see snow here in January, no snow in July, say. Okay, great. Yeah, so we're building out this example from PyTroll, and it's going to animate Hurricane Florence as it moves across the Atlantic Ocean. In this case, it's going to be using data from the GOES satellite. So GOES is it's a geostationary satellite, a pair of them actually taking pictures of the Earth. So there's a whole bunch of information on GOES here in the data catalog. We'll just go through this example here. NOAA has a storm tracks database, which gives like the positions and actually a whole bunch more data for I think any hurricane or tropical storm, maybe in the world. We're just going to grab out the one for GOES. So it's a netcdf file, so it's like a bit difficult to use, but once you know the right storm ID, which you can look up in the separate file, I found the storm ID for Hurricane Florence, and then we can select just the data that it uses that storm ID. and then X-ray to filter it down to just this data for Hurricane Florence. So there's a whole bunch of data variables for Hurricane Florence that's tracking things, even things like wind speed and the direction. We're not going to use any of that. We're just trying to find the position of it at some particular time. So we're going to grab out the time attribute and then the longitude and the latitude. And we'll put that into a GeoPandas geodata frame. We can plot the data that we have. So you can see it started here over on the west coast of Africa and made its way. And we're going to be animating this little section here before ultimately it went on to North Carolina and South Carolina. Okay. So this is all we need for our search that we need to find the actual imagery. Okay, we have our bounding box and we have our date time that we care about for this animation. So again, we'll use the STAC API here to do our query. In this case, we're using GOES CMI, the cloud and moisture imagery, passing in our bounding box, which we just discovered from that hurricane tracks database, and then the date time. Final thing here we're going to query on. So GOES has it's capturing several different areas and different resolutions at the same time. So it has a picture of the whole half disk of the Earth, and then the continental United States, and then finally a mesoscale, which is kind of like a smaller zoomed in area. So we want just the mesoscale images for this area and for this date time. GOES is it has a strange projection. It's some geostationary orbit. So we can't use STAC for it. So we do need to use Rio X-ray, which is a great library for reading in raster data into X-ray. It knows how to deal with all the weird coordinates reference systems that GDAL can use, because that's what it uses under the hood. In this case, here's the first band. So we have successfully identified the storm. We found it. And this is the blue band. Okay. All right, so now we're going to read in a bunch of data. We have several bands here. So 3 bands again that we're going to read in. We're going to get the time as well. And then we're going to read this in. So for each of the time steps, we have 3 bands. So this will take 15 to 20 seconds. Again, this is just reading in the metadata. Since it's not using STAC, we do have to actually open up each of those few hundred files, however many it is, maybe 5, yeah, so 600 or so files, 500 or 600 files. So that completed in 12 seconds, not too bad. And then we can actually persist the data. This will actually be even slower or faster because it's happening on our cluster in parallel. Okay, we're gonna make another pretty picture. That's not the only thing we do, but it's nice to make pretty pictures. So GOES doesn't have a green band, but you can use some band math to simulate it as a combination of the red, near infrared, and blue bands. So we'll call this new thing our green band. And then there's a gamma correction. I think this basically makes the picture brighter, a bit brighter. Okay, so we'll do that band math and then normalize it, gamma correction, and then compute it. So that's happening on the cluster. Now we have it back locally, and this will be one of our images. Okay, so that's gone from this red, near infrared, and blue, and gotten an RGB, a red, green, blue image out of it. Matplotlib, super flexible. It's a little bit of boilerplate to set up this animation, but it does what we need. We're still using X-Ray's higher level plotting APIs, which is great. We're able to plot onto our figure, add some text. So this will handle we'll have a little text at the bottom saying what is the current timestamp. And then we just churn through the animation. So each time step will grab out that slice, and then set the data on our image. So it doesn't take too long to make our image.
Hey, Tom, just a quick heads up. We have about 5 minutes left. I don't see any questions for now.
Great, thanks. Yeah, and so here is our movie. I think it's worth pausing, enjoying this for just a minute. I'm sure there's some scientific value that can be gleaned from this, but it's also fun to look at. Interesting to look at. Perhaps not fun for the folks in North Carolina that this actually hit. Okay, so that's our workflow there. And so yeah, pretty picture, that's great. Probably could get some science out of that. But in terms of the actual workflow here, I want to highlight a couple things. Is like once we found the right bounding box and the date time, is pretty straightforward to go from that to the actual images. Searching for the actual images was straightforward using the STAC API. And then again, we're building on top of libraries like Xarray and Dask. So using those name indices was great. It's much nicer to use red, near infrared than like 0 and 1. And we're able to parallelize our computation with Dask. Okay, I believe that is it. Yeah, so a couple links here, planetarycomputer.microsoft.com. You can go there, check out anything. Like I said, the STAC API and the data you can use anonymously. If you want an account on the Planetary Computer Hub to do that, like cloud native computing, you can fill out an account request form there. And then the notebook that I went through and these slides are there at the at my GitHub. Cool.
Thank you very much, Tom. Very exciting talk. And we had something to look at. MM wants to know, how much do the 64 instances you spun up cost in Azure?
I would have to check the exact pricing. The nice thing is we're using spot nodes. So those could have been preempted by Azure if someone comes along with a higher bid or whatever. So it's actually not too bad when you're using spot pricing.
Okay, Matt wants to know, general question, any thoughts on Dask versus PySpark?
Yeah, I don't know. I'm a Dask developer, so definitely biased here. Dask is nice because it handles n-dimensional arrays, which last I checked weren't as common in like the Spark ecosystem. And I also have not really used Spark extensively, so it's hard to say. I will say the Dask documentation has a pretty good overview of this exact question. I'll get the link for the chat, but anyway, like I would say both of them do similar things pretty well. So use probably whatever you're most familiar with is a good default position.
Okay, and Matt specifically asked for this sort of application.
Yeah, so on this, so we're doing some n-dimensional things. So maybe like that's a bit more natural in like Xarray and Dask, but we're also, I'm sure you could do this with Spark if you chunk it up appropriately. And there are definitely libraries, nice libraries like raster frames is able to read in stack metadata into its data model. Similarly to how STAC handles it. So that from that point of view, for the STAC side of things, that's well supported in both.
Cool. Well, thanks for your talk and thanks for being part of PyData Global 2021.
Thank you.